कहता how are you waiting for Unacademy NEET English? You should go to my live stream अगर इशन कर सकें. Hello and good evening everyone guys. I welcome you all once again to this wonderful channel by Unacademy NEET English. I believe that you all are doing great. Well, my name is Kar Khurshid Alam. You can also call me KK sir. Before we move ahead, I want quick confirmation that if you can see me clearly and hear me clearly, let me know in the chats quickly. Let me know in the chats quickly. Let me know in the chats quickly. All right, I believe we are live now and super excited to start today's session. So my dear lovely students, today we are going to take one of the amazing session never like before. In organic chemistry, we are taking on top 20 concepts, and in today's session we will be discussing few among them. I want to ensure you that your NEET paper will be around these concepts only. So I would want you all to be with me till end of this session. And also I would want you all to mark the attendance by smashing the like button. Do share this stream with everyone around. So without wasting much more time, let's get started with our first concept. Now, our first concept is, have a look, that is halogenation of alkanes. Now, what is meant by halogenation of alkane? It means it is actually introduction of alkanes. It's actually introduction of halogen to alkanes. It is introduction of halogen to alkanes. Point number one. This is our point number one. Point number second, you must remember that this reaction is an example of free radical substitution reaction. Point number 3, as this is the free radical substitution reaction, so intermediate of this reaction will be obviously free radical. So point number 3 is intermediate of this reaction is free radical. After that, remember, if we are having an alkane, when we treat halogen to an alkane, this reaction is basically taking place this reaction is basically going to take place in either what we call light, which can be written like HNO or UV, and what we call heat, or we can simply say it takes place in presence of heat. So this reaction generally takes place in presence of either light or heat. What we have to do is we have to replace this H of alkane, and here we will introduce X. So we get simply an alkyl halide from alkane, and side product will be HX. Now, the question is, this reaction is free radical substitution. How actually it takes place? Have a look. Have a look. So I mean to say, we will discuss its mechanism little bit, because mechanism of this reaction is very, very, very important. Have a look. First of all, as this is free radical reaction, this reaction gets completed in 3 steps. Free radical reaction generally gets completed in 3 steps. Gets completed in 3 steps. Step number one is always initiation. Step number 1 is always initiation. Now the question is, what happens during initiation? During initiation, our reagent always form radical. Now the question is, in our reaction, which is reagent over here? We know this is the substrate of the reaction, and this is the reagent of our reaction. So what will be the first step? That is initiation. That means our reagent will form free radical, either in presence of light or in presence of heat. Homolytic cleavage takes place between X and X, and it results in the formation of a free radical or odd electron species. Now, this free radical will attack one substrate now, and our second step will be now propagation. That means in second step, free radical formed from attacking reagent or reagent will attack now to the substrate. I mean to say, now our substrate, that means alkane, will react with this radical. As we know, this radical needs 1 electron, and because of that, it cleaves this C or R H bond in such a way so that homolytic cleavage takes place. And we know during homolytic cleavage, radicals will be formed. So H radical will be formed as well as C radical or R radical will be formed. Whenever H radical is formed with R radical or any other radical, H radical is more reactive. That clearly indicates this X will combine with, I mean to say, H. So in our first step of propagation, we will get like this, R radical plus HX. Now, in second step of propagation, this R radical formed in, I mean to say, first step, it will react with another molecule of our reagent. And now this radical will cleave this XX bond homolytically, and this X will combine with R, and we get Rx, that means our product, plus X radical. Now, our product generally is formed during propagation step when it's, I mean say, free radical reaction. After that, we want to stop now the reaction because our product has been formed. So we want to stop the reaction. But we know for stopping the reaction, that means termination. All the radicals formed in propagation step must combine together so that there will be no radical left. Because if radical is left, then it will once again attack the substrate and reaction will continue. So to stop the reaction, we will combine all the radicals formed in, I mean say, propagation. That means R radical, which is formed in propagation, will combine with similar radical, and it will result in the formation of RR. That means R radical, one of the possibilities is, can react with another R radical and can form RR. Similarly, one of the possibilities is that X reacts with X and it will result in the formation of X2. Similarly, this R and X radical, R radical and X radical can combine and they can form Rx. That means our product. But our major product will be formed during propagation step. So in initiation, reagent forms a radical, and in propagation that radical will attack substrate, forms a new radical, then new radical reacts with reagent once again and results in the formation of what we call a product. So product formation generally takes place in, I mean to say, propagation step. And remember one more thing, that all the steps of propagation must be exothermic. That means thermodynamically favorable condition is that all these steps must be exothermic. I hope this is clear till now. Now let me know in the chats, am I clear till now? Because I will simply touch these concepts in such a way so that no question can bother you in, I mean to say, your upcoming NEET examination. Now let me know, am I clear? Till now? Just a moment, give me a second and let me know in the chats. Quickly. Let me know in the chats, my dear lovely students. Okay, so this is clear. Remember, this mechanism is very important for you. That's why I have shown this mechanism as well. Now, have a look. After that, this is the mechanism of the reaction. Now, the question is, if we use halogens, so among halogens, which halogen will be the most reactive towards this reaction? So remember, among halogens, reactivity order. So another point is like this, that their reactivity order will be. Have a look. Fluorine is very reactive as compared to chlorine. Chlorine is very reactive as compared to bromine. And bromine is very reactive as compared to iodine. So this order, you have to remember this order. After that, another point, what you have to remember is that among hydrogens, order of reactivity towards free radical reaction or towards this reaction, order of reactivity will be 3 degree hydrogen greater than 2 degree hydrogen greater than 1 degree hydrogen. This order is basically based on stability of the carbon free radical formed when carbon and hydrogen bond is broken. Have a look. Have a look. Whenever carbon hydrogen bond is broken, it results in the formation of a carbon free radical. So if this is tertiary carbon to which tertiary hydrogen is attached, then it can form tertiary radical. Secondary carbon attached to, secondary hydrogen attached to secondary carbon, so is known as secondary hydrogen. If secondary hydrogen is removed, it results in the formation of secondary carbon free radical. And primary hydrogen, if removed, results in the formation of a primary carbon free radical. But we know tertiary carbon free radical is more stable, then secondary carbon free radical, then primary carbon free radical, and reactivity of hydrogens is directly proportional to stability of their carbon free radical. That's why I have written over here 3 degree hydrogen, 2 degree hydrogen and 1 degree hydrogen. After this, we will start our first reaction, that is chlorination of alkane. Chlorination of alkane. Have a look. Now, what is meant by chlorination of alkane? We know halogenation means introduction of halogen. So, chlorination of alkane means introduction of chlorine to alkane. Now, if we take a simple example like this, CH4 plus Cl2. And if reaction takes place in presence of light, say for example UV or HNu, now, or in presence of heat, what will happen? I have shown you the mechanism right now. Now, what will happen? Once again, have a look towards mechanism. Now, what will happen? Radicals will be formed here. As this is Cl2, so it can form Cl radical. After that, that Cl radical will abstract hydrogen or will attack this substrate and will abstract hydrogen. Then CH3 radical will be formed. Then that CH3 radical will combine once again with Cl and results in the formation of CH3Cl. In a nutshell, hydrogen will be replaced by 1 chlorine, so its product will be CH3Cl and HCl. Now let me know, if this chlorine is taken in excess, can I say it will react with this CH3Cl? I mean, say product of first reaction, this chlorine will react with the product of first reaction under similar conditions. But if chlorine is taken in excess, then what will happen? Another hydrogen will be replaced. So it will result in the formation of CH2Cl2 plus HCl. After that, what will happen? This CH2Cl2 formed in above reaction will once again react with Cl2. Then it will result in the formation of CHCl3 and then HCl. Finally, this CHCl3 reacts with chlorine and results in the formation of CCl4 plus HCl. Now, this CCl4 cannot react further with Cl2 as it does not have any hydrogen. So, can I say like this? That means if methane is taken with chlorine in excess, what will be the products formed over here? Here, product formed can be CH3Cl, it can be CH2Cl2, it can be CHCl3, or it can be CCl4. Now, can I say that either one hydrogen or more hydrogens of, alkane will be replaced if halogen is taken in excess? So, can we say halogenation of alkane, chlorination of alkane in presence of light or heat is basically a polyhalogenation reaction? Now, let me know in the chats, am I clear till now? Let me know in the chats, am I clear till now? You have to be with me because we are going to solve few questions or different types of questions as well. Because we are not going to, discuss concepts only. We will also solve questions as well. Let me know in the chats. Today's session is very, very, very important if you want to score more than 95% or more, or we can simply say 100% in organic chemistry. Okay, that's great. Now, after this, Note down these points. Note down these points. If chlorine is taken in excess, if Cl2 is taken in excess, then in above reaction, CCl4 will be the major product. CCl4 will be the major product. Will be the major product. Then point number second, if CH4 is taken in excess, if CH4 is taken in excess, then CH3Cl will be the major product in above reaction. Will be the major product in above reaction. Why? Because if Cl2 is taken in excess, then Cl radicals will be in excess and they will replace all hydrogens of methane and will form CCl4. Similarly, if methane is taken in excess, then CH3 radicals will be, in excess. At that time, CH3Cl will be the major product. After that, you must know one more thing. Say, for example, you are having a question like this. Methane upon chlorination in presence of light or heat results in how many number of monochloro derivatives? Number of monochloro derivatives. How many number of monochloro derivatives? Now, actually, this is very important question, that you have an alkane given in the question. Now you have to find out number of monochloro derivatives. So how to solve this question? For that you have to remember this one. Number of monochloro derivatives. Number of monochloro derivatives formed from an alkane. Formed from an alkane during halogenation is always equal to number of different types of hydrogens. Number of different types of hydrogens. Number of different types of hydrogens present in an alkane. Present in an alkane. That means you must know how many different types of hydrogens are present in an alkane. Now, for this, have a look how to, solve these types of questions. Have a look. Suppose you are having methane. Remember, in methane, there is only one carbon and hydrogens attached to one carbon will be always one type of hydrogen. So, it's having only one type of carbon, hence it's having only one type of hydrogen. Similarly, if you are having CH3, it's having two carbons but type is only one. Hence, all these 6 hydrogens are one type of hydrogen. Similarly, if you are having CH3, these CH3 and CH3, this carbon and this carbon, it's only one type. That means all 6 hydrogens are type 1 hydrogen or type A hydrogen, and this carbon is type B carbon. Hence, these types of hydrogens are type B. That means in total, this is having 2 type of hydrogen. Similarly, if I write down like this, CH3, CH2, this is having once again 2 types of hydrogens. 2 types of hydrogens. 2 types of hydrogens. 2 types of hydrogens. If you have a structure like this, it's having 2 types of hydrogens. A is this type, B is this type. So this is having 2 types of hydrogens. Similarly, if you are having a structure like this, you know that this structure, I mean say 2-methyl butane is having 4 types of hydrogens. So it's having 4 types of hydrogens. Basically, types of hydrogen depends upon types of carbon, and types of carbon depends upon the groups attached to a single carbon. Say for example, this single carbon is having 3 hydrogens attached to it, and on 4th side it is CH, CH3, CH2, CH3. Similarly, this is having 3 hydrogens and CH, CH3, CH2, CH3. That means the surrounding of this carbon and this carbon is same, hence hydrogens attached to them are also same. Similarly, if you are having a cyclopentane, this is having all these hydrogens, all these carbons are of same type, hence this is having only 1 type of hydrogen. So first of all, you must know how many different types of hydrogens are there. After that, suppose this question, this is the question. Suppose this is the question. Question is, how many monochloro derivatives will be obtained now? How many monochloro derivatives will be obtained now? But we know this is having 4 different types of hydrogens. So this is having 4 different types of hydrogens, like this is A type, this is A type, this is type B, this is type C, this is type D. Then remember, we will be having 4 different monochloro derivatives like this. Yani we have to remove 1 hydrogen and we have to replace that hydrogen by chlorine. But we have to remove hydrogen from either A or from B position or from C position or from D position. I have replaced this hydrogen, I mean say from this A position by chlorine. After that, this will become first monochloro derivative or chloro product. So this is A. Then after that, B products will be like this. CH3, C, CH3. Now I will replace hydrogen at B by chlorine. Then it is like this. So this is the product B. After that, I can replace C hydrogen by chlorine. Then its product will be like this. So this is C product. After that, I will replace hydrogen at position number D or from carbon D. Then this will be what we call our product. Now, let me know in the chats, is this clear? Is this clear? But remember, this formula is applicable only excluding stereoisomers. This is applicable excluding stereoisomers. That means here, product will be depending upon number of different types of hydrogens like this. Like this, this was having 4 different types of hydrogens, hence 4 different products are formed, but excluding stereoisomers. Let me know in the chats, am I clear? Let me know in the chats, am I clear till now? Am I clear till now? Let me know in the chats quickly. Let me know in the chats quickly, because this is very, very, very important session for you. Let me know in the chats. Okay, thank you, Asiba, thank you, Jaya, thank you, Kirthana, thank you. Okay, great. Now, after this, remember here 4 products will be formed, but excluding stereoisomers. Excluding stereoisomers, 4 products are formed. But sometimes question will be like this: how many total products will be formed, or how many products will be formed including stereoisomers? For that, you have to check here that this carbon is what we call a chiral carbon. Similarly, this carbon is known as what we call a chiral carbon. And we know whenever a molecule is having 1 chiral carbon, at that time products, I mean say isomer forms will be 2. One will be this A, another will be its image. I mean say its enantiomer, its mirror image, non-superimposable mirror image. I mean say its enantiomer. Similarly, this will be C plus its image means its enantiomer. Now, in total, products formed will be 1 and its image, that means 2. this is 3, this is 4, this is 5, and this is, I mean to say, 6. So, including stereoisomers, there will be 6 products. So, including stereoisomers, products formed will be 6. So, this is including stereoisomers. Product formed will be 6. After that, you must know this one. You must know this one. Tertiary hydrogen is more reactive than 2 degree. 2 degree hydrogen is more reactive than 1 degree. We know that. But what is their relative reactivity? Relative reactivity is like this. 5 is to 3.8 is to 1. But this reactivity is of tertiary, secondary and primary hydrogens with respect to chlorine. With respect to chlorine. That means this 3 degree hydrogen is 5 times more reactive than 1 degree hydrogen as per chlorine is concerned. Similarly, 2 degree hydrogen is 3.8 times reactive with chlorine as compared to 1 degree hydrogen. Now, if I say in this question, if I say what will be the percentage of this, percentage of this, percentage of this, or percentage of this? Have a look. I will write down how many type A hydrogens were present in this. 3 and 3, 6. That means I will write down type A hydrogen. They are 6 in number. Similarly, type B hydrogen. Type B hydrogen. How many type B hydrogens were present? Only one. Only one. How many type C hydrogens were present? Have a look. They were 2. Have a look. C 2 and D 3. So type D hydrogen are what we call 3. Now, which type of hydrogen is this A? A is basically attached to a primary carbon. Hence, these are 1 degree hydrogens. Type B is attached to 3 degree carbon. Hence, this is known as 3 degree hydrogen. Type C is 2 degree hydrogen and type D is 1 degree hydrogen. That means this is 2 degree hydrogen and this is 1 degree hydrogen. And we know reactivity of 1 degree hydrogen is 1, reactivity of 3 degree hydrogen is 3, is 5, and reactivity of 2 degree hydrogen is 3.8, reactivity of 1 degree hydrogen is 1. But 1 degree hydrogen type A is 6 in number. So I will write down multiplied by 6. Here it's only 1 in number. So I will multiply this by 1. This is 2 in number. So I will multiply this by 2. And these types of hydrogens are 3 in number. So I will multiply this by 3. So the answer is 6. Here it is 5. Here it is 7.6. Here it is 3. In total, reactivity of all the hydrogens will be 21.6. Are you able to understand what I am saying to you? Now, here, what will be the percentage of this? Total is 21.6. So its percentage will be 6 divided by 21.6 multiplied by 100. So you can calculate the percentage very easily. Similarly, here it will be 5 divided by 21.6 multiplied by 100 and you can get percentage of this as well. Similarly, it is 7.6 divided by 21.6 multiplied by 100. Similarly, here it will be what we call 3 divided by 21.6 multiplied by 100 and percentage will be here. But have a look. We know denominator is same everywhere, but numerator is very much high over here as compared to others. That means this value will be obviously more and this is type C. That means if we replace, have a look, if we replace type C hydrogen, that means if we replace type C hydrogen, product will be this and this product will be major product. This product will be the major product. Now listen carefully. That product which is formed from this tertiary carbon radical by removing tertiary hydrogen. Because if we remove 1 degree hydrogen, 1 degree carbon free radical will be formed. If we replace or remove what we call tertiary hydrogen, tertiary carbon free radical will be formed. And if we remove secondary hydrogen, secondary free radical will be formed. Now let me know in the chats which type of radical is most stable. Let me know in the chats. Is this 1 degree? Is this 2 degree? Is this 3 degree? Let me know in the chats quickly. Let me know in the chats quickly. Which type of, I mean to say, radical is more stable? Is this 3 degree radical? Is this 2 degree radical? Exactly, Sibu. It's 3. Great, great, great. Very good, very good, very good. Nice. It is 3 degree radical. That means 3 degree radical is more stable. Means the product formed from 3 degree radical should be, I mean say, major product. But here, product formed from 2 degree radical is major product. So remember forever, reaction. Remember forever, reaction in which, remember, reaction in which product, in which, I mean to say, major product, in which major product, reaction in which major product is formed from most stable carbon free radical, from most stable carbon free radical, is called selective reaction. Is called selective reaction. But let me know, can I say during chlorination major product can be obtained from that radical which is not most stable radical like this? Hence, this is not what we call a selective reaction. Hence, we can simply remember this point. This is very, very important point. Chlorination is a non-selective reaction. So, chlorination is a non-selective reaction because its major product can or cannot be formed from most stable carbon free radical. So, chlorination is a non-selective reaction. And remember, selectivity is basically, or this selectivity is actually inversely proportional to reactivity. That clearly indicates if this is more reactive than chlorine, if chlorination, I mean say chlorine is more reactive than bromine, that's why it's less selective as compared to bromine, or we can say bromine will be more reactive as compared to chlorine. I mean to say, if we talk about bromination of alkane, if we talk about bromination of alkane, bromination of alkane takes place in similar manner. Bromination of alkane, my dear lovely students, remember, takes place in, this reaction takes place in similar manner. This reaction takes place in similar manner. As that of chlorination. But the only thing is, number one, bromination is more selective. Bromination is more selective than chlorination. I mean to say, if the same alkane undergoes bromination, remember, if same alkane undergoes bromination, then the major product formed will be always from more stable carbon free radical. That means directly you can say, as this hydrogen, after removing this hydrogen, carbon free radical will be most stable over here. Hence, product formed from this hydrogen will be more, in percentage, that means that will be major. That means if reaction takes place with bromine, here it will be bromine and product B will be at that time the major product. So that's why bromination is basically a selective reaction. After that, one more thing is like this, that 3 degree hydrogen, 2 degree hydrogen and 1 degree hydrogen relative reactivity is like this. 3 degree hydrogen is 1600 times more reactive than 1 degree hydrogen, and 2 degree hydrogen is 82 times more reactive than 1 degree hydrogen. But when these hydrogens react with bromine, I mean say this relative reactivity is with respect to bromine. I hope this is clear to each and everyone till now. I hope this is clear to each and everyone till now. Let me know in the chats quickly. Am I clear till now? Is chlorination and bromination clear to each and everyone? Let me know in the chats quickly. Let me know in the chats quickly, my dear students. Let me know quickly. Let me know in the chats. Okay, let me switch off few lights because here is very much issue of say lights. So let me switch off few lights. Give me a second, my dear lovely students. Give me a second. Are you able to see the board clearly? Let me know. Are you able to see the board clearly? Okay. Now, next is fluorination. Next is fluorination of alkane. Fluorination of alkane. Just remember one thing over here, that this reaction is too violent to be controlled. This reaction is too violent to be controlled. And the reason is high reactivity of fluorine. Because of that, reaction becomes highly exothermic, and that's why this reaction is too violent to be controlled. If this reaction is too violent to be controlled, so we can simply say direct fluorination of alkane is not possible. 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 So, after that, we will be having iodination of alkane. We will be having iodination of alkane. For this, remember that direct iodination of alkane is not possible. Direct iodination of alkane is not possible because reaction is reversible. Because this reaction is reversible, and reason is formation of HI. Formation of HI. I will replace H, it will result in the formation of alkyl iodide, but this HI is also formed there and it acts as a reducing agent, and it will simply convert this alkyl iodide back to alkane. So direct iodination is not possible. Now, direct iodination can be possible only. Direct iodination can be possible only if we remove this HI, and this HI can be removed if we use oxidizing agents like HiO3, HgO or HNO3. So these will remove HI. Hence, if HI is removed, reaction will proceed towards forward direction. That means we can simply form alkyl iodide from alkane at that time, or at that time direct iodination is possible. So this was all about concept number 1. Now have a look. Here are few questions. The major product in the monobromination. It is monobromination, and we know bromination is a selective reaction. And if bromination is a selective reaction, product formed will be always, major product will be always formed. Major product will be always formed from most stable carbon-free radical. Most stable carbon-free radical. So major product will be always formed from most stable carbon-free radical. Now, this is monobromination of what? 2-methyl butane. What is 2-methyl butane? 2-methyl butane is this one. Now let me know in the chats quickly. Let me know in the chats quickly. If this is A, this is also A, this is B, this is C, this is D. Can I say A and this A, I mean say these are 1 degree carbons and hydrogens attached to them will be 1 degree hydrogen. B is at 3 degree carbon and hydrogen attached to this is 3 degree hydrogen. Now, this is what we call a 2 degree carbon, hydrogen attached to this is 2 degree hydrogen. This is 1 degree carbon, hydrogen attached to this will be 1 degree hydrogen. Now, let me know in the chats, which type of carbon will remove hydrogen and form more stable carbon-free radical? A, B, C or D? Let me know in the chats quickly. A, B, C or D? A, B, C or D? Zunera, exactly Zunera. Pujari, great. Chandini, exactly. Okay. Viramani, great. So, as we know, this will form more stable carbon-free radical. Hence, the product, major product will be like this. Major product will be like this. We will replace this H by Br and major product of this reaction will be this. Have a look. So what is the name of this compound? This is 2-bromo 2-methyl butane. 2-bromo 2-methyl butane. Is there any option 2-bromo 2-methyl butane? So this is our option. I hope this is clear to each and every one. After that, how many products? But here question is including stereoisomers. This is the question asked in last year NEET 2025. These are asked questions basically. So how many products including stereoisomers are expected from monochlorination of the following compounds? We have done this. Have a look. We have done this. How many monochlorinated products have been formed including stereoisomer from this? Its number is 6. So this is also the same question asked in NEET 2025. So the answer is 6. I mean say option number 4. After that, which statement about free radical halogenation is, but remember this is incorrect. This is not correct. This is incorrect. Now have a look. First statement is fluorination is highly explosive and uncontrolled. This is exactly correct, but we have to find out incorrect. After that, iodination is reversible, exactly, and requires an oxidizing agent. This is also true. Bromination is more selective than chlorination. This is also true. Then chlorination gives equal amounts of all possible products. No, this is wrong. We have to find out wrong answer or incorrect answer. So this is our option. After that, we are having another very important concept, and that is electrophilic addition reactions. Let me tell you, these reactions are characteristic properties. These reactions are characteristic properties of alkenes and alkynes. Now, and remember these electrophilic addition reactions, in case of say alkenes, we can simply say these can be taking place via classical carbocation. So electrophilic addition reaction can take place via classical carbocation. That means intermediate of such reactions will be classical carbocation or via non-classical carbocation. Via classical carbocation or via non-classical carbocation. Now what is meant by classical carbocation? Classical carbocation means positive charge on carbon is fully developed. Positive charge on carbon is fully developed. Point number two is When such carbocations are formed, rearrangement can take place. So during such reactions, rearrangement can take place. Now, how will we identify that this electrophilic addition reaction takes place via classical carbocation or via non-classical carbocation? For that, remember, highly polar reagents generally show this reaction. Highly polar reagents like HX, H2SO4, that means HOSO3H, I mean say H2SO4. Similarly, HOH means water, HSH means hydrogen sulfide, HSR means thioalcohol, HOR means alcohol, HOC double bond O and R, I mean say carboxylic acid, etc. When reagents are such that there is high electronegativity difference between positive part and a negative part, that means highly polar solvents should be there. This positive charge on carbon is not fully developed. If charge is not fully developed, we will simply say no rearrangement takes place. No rearrangement takes place. And number next is reaction takes place between. This reaction takes place between, I mean say this reaction is shown by, basically you can say non-polar or less polar reagents. Generally in which electrophile or electrophilic part or electrophilic site contains a lone pair. Like X2, I mean say halogen. I can say HOX, I mean say hypohalous acid, that means halogen in water. Similarly, NOCl, nitrosyl chloride or Tilden's reagent, so on and so forth. Now, after this, let us start with the concept of classical carbocation. Now, have a look. We will simply discuss mechanism of classical carbocation or classical carbocation mechanism. Have a look. Because once you understand the theory or concept, then it's very easy to solve organic chemistry questions. Now, have a look. First of all, if this is an unsymmetrical alkene, have a look. Suppose this is an unsymmetrical alkene and we react a reagent with this like this. But remember, this reagent should be highly polar. So, if let us suppose this is highly polar reagent. And for that, we must remember this one. If this is an electrophilic part, this is nucleophilic part, then it can be either HX, I mean say halogen acid, it can be either HOSO3H, I mean say H2SO4, it can be either H and then OH2 with a positive charge, I mean say H3O positive, but in H3O positive, it is H positive of acid which acts as an electrophile and water will act as a nucleophile. Similarly, if I write HOR, that means alcohol, if I write HSH, if I write HSR, we can write HOC double bond O and R. So anyone can be, I mean say here used. So remember these as well. After this, now what will happen over here? Have a look. In presence of this reagent, remember, this electrophilic part will be attached to either this carbon or to this carbon. I mean to say, if electrophilic part is attached to this carbon, here it will be a carbocation and nucleophile will be lost over here. This step is slowest step, hence rate determining step of the reaction. If this electrophilic part goes to this then it will result in the formation of a carbocation like this. But remember, this is more stable carbocation and this will become less stable carbocation. Now, remember my dear lovely students. Now what will happen? In second step, nucleophile will attack now. Obviously, nucleophile attacks electron deficient site. Now, nucleophile will attack carbocation. But first of all, if this carbocation undergoes rearrangement, because after rearrangement, we have to see whether this carbocation becomes more stable or not. So, if after rearrangement, carbocation becomes more stable, we have to rearrange carbocation first. After that, after forming most stable carbocation, nucleophile will attack. Nucleophile will attack to this carbocation and it can form a product like this. Now tell me, can I say during this reaction, electrophile and nucleophile has been added across carbon-carbon double bond. So this is addition reaction. But among electrophile and nucleophile, it is electrophile which is added first to this substrate. Hence, this is electrophilic addition reaction. And this reaction takes place via a carbocation which is fully developed. That means classical carbocation mechanism. Now have a look. If HX is here, then first you have to add H positive, then X minus will act as a nucleophile and that will attack on what we call a carbocation. Similarly, all reaction takes place in similar manner. But here you have to remember, this is substrate. You have to remember over here, and that is when substrate is unsymmetrical, reagent is unsymmetrical. That means electrophilic part is something different than nucleophilic part. That means if this is reagent is what we call unsymmetrical and substrate is unsymmetrical, we have to add unsymmetrical reagent to unsymmetrical substrate according to a rule, and that rule is known as Markovnikov's rule. So Markovnikov's rule is applicable only if reagent is unsymmetrical and substrate is unsymmetrical. At that time, unsymmetrical reagent is added to unsymmetrical substrate according to a rule known as Markovnikov's rule. Now, let me write down this point because this is very, very important. Whenever reagent is unsymmetrical, and substrate is unsymmetrical, then addition of unsymmetrical reagent to unsymmetrical substrate takes place according to Markovnikov's rule. It takes place according to Markovnikov's rule, which states that negative part of reagent or addendum, basically reagent here is basically the molecule to be added, and molecule to be added is known as addendum. Negative part of addendum, that means molecule to be added, goes to that carbon-carbon multiple bond, I mean say either double bond or triple bond. So carbon-carbon multiple bond which is having lesser number of hydrogens, which is having lesser number of hydrogens. I mean to say, if we are having a reaction like this, CH3, CH, double bond CH2, then we will add either HX. HX can be HF, HCl, HBr, HI, but remember, among HX, HI is more reactive than HBr, HBr is more reactive than HCl, HCl is more reactive than HF. So, if any HF, HCl, HBr, HI is used, then negative part of this addendum means X goes to that carbon-carbon double bond, which is having lesser number of hydrogen. So it will be like this. So X will go here and positive part goes to that carbon-carbon double bond, which is having more number of hydrogen. So this is known as Markovnikov's rule. And product will be according to Markovnikov's product. So product will be according to Markovnikov's rule. Hence this product is known as Markovnikov's product. But remember, reactivity among HX will be HI greater than HBr greater than HCl greater than HF, or we can say HF is very least reactive, so hence we will not react alkene with HF. So reactivity among HX will be this. Am I clear till now, my dear students? Am I clear till now? Similarly, if you use here H2SO4, then H will go to this, HSO4 minus or OSO3H minus, negative part will go to this. Similarly, if you use H2O, H will go to this and OH will go to this. So I mean say any electrophilic addition taking place via classical carbocation is like this. I mean say like this. Mechanism is like this. But here, this will be the major product, because it will be formed from more stable carbocation, and this will be the minor product. It will be formed from less stable carbocations. But remember my dear students, these two are having same molecular formula, but position of electrophile and nucleophile are different. Hence these two are isomers. So remember, when you start reaction with unsymmetrical alkene, we can get, in this reaction we can get isomers. One isomer will be present in major quantity, another isomer will present in minor quantity. Such reaction is also known as what we call regioselective reaction, if these two are, structural isomers. Now, after that, so can I say these all reactions are completed over here? But we have to remember a very important point, that is like this. Exceptions to Markovnikov's rule. Exceptions to Markovnikov's rule during these reactions. Exception number one is if rearrangement takes place during the reaction. If rearrangement takes place. If rearrangement takes place. Have a look. If we are having an alkene like this, this is a unsymmetrical alkene. This is an unsymmetrical alkene. Now I will show the mechanism for major product only. Have a look. Because here major product was formed according to Markovnikov's product. Now here major product is formed but not according to Markovnikov's product. Have a look. If I write HX, what will happen? H will be simply added to this carbon and X minus will be lost, and this step is rate determining step, and we will get CH3 single bond C CH3, then CH3, then it will be CH having a positive charge, then this is CH3. But we know in this carbocation rearrangement takes place, so 1,2 methyl carbanion shift takes place. When this methyl carbanion is shifted, then it will result in the formation of more stable carbocation. So it will result in the formation of more stable carbocation. Finally, X minus, nucleophile, will attack to this more stable carbocation. Reaction is very fast and our major product will be like this. Major product will be like this. have a look, my dear students. What was the statement according to Markovnikov's rule? Negative part goes to that carbon-carbon double bond which is having lesser number of hydrogen. That means X should be here, added to this carbon, and H should be added to this carbon. So that is expected according to Markovnikov's rule. But product formation is this one. So can I say this is an unexpected product? This is not the product formed according to statement of Markovnikov's rule. Hence, we can simply call this product as rearranged product. So can I say major product in this reaction is not according to the statement of Markovnikov's rule? Let me know in the chats quickly. Am I clear till now? Am I clear till now? बेटा अगर रिएक्शन मीडियम में पेरोक्साइड आ गया तो क्या मैकेनिज्म पूरा चेंज हो जाएगा? वो भी अभी दिखाऊंगा, बिकॉज दैट्स अनदर कॉन्सेप्ट, and that concept is known as peroxide effect or Kharash effect. But where we have to apply that effect, I will show you that also. So just wait and watch. Just wait and watch, my dear lovely students. Now, after this, one is if rearrangement takes place, at that time statement of Markovnikov's rule gives one product, but in actual sense major product will be another. That means here, I mean to say, Markovnikov's rule, according to Markovnikov's rule, or we can say here, major product is not according to the statement of Markovnikov's rule. After that, second is, if electron withdrawing group, say for example NO2, is attached to carbon-carbon double bond. Have a look. If we have NO2 group, it's attached to carbon-carbon double bond, then what will happen? What we have to do is, major product will be always from more stable carbocation. So more stable carbocation will be here. I mean to say, this H will be attached to this position, X minus will be lost. Then this is an electron withdrawing group, NO2. This will result in the formation of a carbocation like this. Why? Because this is more stable carbocation. If we form carbocation over here, NO2 will destabilize that carbocation because NO2 is directly attached to that carbon. Hence, we will form more stable carbocation over here. After that, X minus will attack. After that, X minus will attack. When X minus attacks, this is a very fast attack, and we will get our product. And product is like this: NO2, then it is CH2, then it is CH2, then it is X. Now, can I say negative part of this should go to that carbon-carbon double bond which is having lesser number of hydrogen? That means X should be attached to this according to statement of Markovnikov. But X is not attached to this, X is attached to this. That means here product is not formed, major product is not formed according to the statement of Markovnikov's rule. I hope this is clear to each and every one there. So this was what we call, I mean to say, electrophilic addition because of classical carbocation. Now we are having electrophilic addition where non-classical carbocation. That means mechanism of electrophilic addition reaction where non-classical carbocation. Now have a look. This is very, very, very important reaction. Have a look. I will show you the general mechanism. So that you can understand each and every non-classical carbocation mechanism reaction. Now, this is an unsymmetrical reagent. Now, if we react it with a reagent which is either non-polar or less polar, and remember, this electrophilic site must have a lone pair over here, then reaction will take place via non-classical carbocation. How? Have a look. It will attack over this, nucleophile will be lost. So this is the slowest step, hence rate determining step of the reaction. But once it forms a bond, this carbon forms a bond with electrophile. This electrophile, with the help of its lone pair, will form another bond with this, I mean to say, carbon. After that, what will be the product? What will be the product? Product will be like this. This is known as cyclic. This is known as cyclic intermediate. This is known as cyclic intermediate. After that, nucleophile will attack. Have a look. Have a look. Nucleophile will attack in a very fast step to this carbon, but not from that side where electrophile is already present. So it will attack from opposite side. When it attacks this carbon from opposite side, ring opening takes place. I mean to say this step is anti-addition step, or this reaction is that reaction in which electrophile and nucleophile will be added across carbon-carbon double bond, but in opposite direction, in opposite sides. If this is present on wedge, that means above the plane, this will be present below the plane. If this is on wedge, that means above the plane, then this will be present on dash, that means below the plane. I mean to say, you have to remember that this reaction or these reactions are anti-addition reactions. These reactions are anti-addition reactions. I hope this is clear. I hope this is clear. Now, have a look. What you have to remember is this one. If you are having halogen, then one halogen is electrophilic part, another will act as a nucleophilic part. Similarly, this is I and Cl. Similarly, I, Br, if halogens are different, then it can be like this, Br and Cl. It can be like this, NO and Cl. This is known as nitrosyl chloride or Tilden's reagent. Tilden's reagent. Remember this. Remember this. Similarly, you can write down other reagents, but you simply remember these, and I will give one more, that is like this. This is Cl and this is OH. Hypohalous acid. Let me erase this Cl. I will write down X because it can be Cl, it can be Br. So HOCl. So this is the electrophilic part and this is the nucleophilic part. That means if you react it with XX, then here it will be cyclic halonium ion. If it is Cl, cyclic chloronium ion. If it is Br, cyclic bromonium ion. That means anti-product will be formed because of cyclic halonium ion. Similarly, if it is X and OH, then here, remember here, what we have to do is in one step, how to perform the product. Have a look. If you are having an unsymmetrical reagent and you will be having reactions like either XX or XOH, or here it's XOH, yes, or NOCl or IBr or ICl or what we call BRCl, what you have to do is, these are the nucleophilic parts. These are the nucleophilic parts. What you have to do is, nucleophilic part, you have to imagine that this is negative part and this is positive part. Nucleophilic part, think, and say that nucleophilic parts are negatively charged parts and these are positively charged parts. Then what you have to do is add these negatively charged parts. Say in unsymmetrical. This is symmetrical. In case of symmetrical, you have to break, pi bond, give one X to one carbon, another X to another carbon. But in these cases, you have to add these negative and positive according to Markovnikov's rule, because there is no rearrangement. So add negative according to Markovnikov's rule. So can I say it will be like this? Negative is generally nucleophilic part, electrophilic part is generally positive except this one. So what will we do? We will simply add nucleophilic part over here and electrophilic part over here, but remember it will be an anti-addition reaction. Now let me know in the chats quickly. Am I clear till now? Let me know in the chats quickly. Am I clear till now? Let me know in the chats quickly, my dear students. Quickly, my dear students. Let me know in the chats. Now, if I am clear, Have a look then. Have a look. Have a look. Have a look. If I am clear, then have a look. There are few more reactions like number one is oxymercuration demercuration, because this reaction is sometimes also known as oxymercuration reduction. What is this reaction? It is simply indirect hydration. It is simply indirect hydration of alkenes. Indirect hydration of either alkenes or alkynes, but at this point of time we are studying electrophilic addition reactions of alkenes. So this is simply indirect hydration of alkene. Have a look. If you are having an unsymmetrical alkene, and to that alkene this reagent is used, HgOAc(2), I mean say mercuric acetate and water. After that, with the help of this, oxymercuration will take place. After that, if NaBH4 is also there in basic medium, then remember demercuration or reduction will take place. But whenever you are having these types of reagents, you have to add at that time water across carbon-carbon double bond, because here substrate is carbon-carbon double bond according to Markovnikov's rule. Now let me know, what will we do? We will break this and we will add negative part to this and positive part to this. I mean to say we have to add water according to Markovnikov's rule. So it will be, addition will be like this. Addition will be like this. I hope this is clear. After that, we are having another reaction, and that reaction is known as hydroboration oxidation reaction. But this reaction is taking place not through, I mean say non-classical carbocation, but it takes place via four-membered cyclic transition state. There is no rearrangement, so no need of mechanism at all. So this is once again an indirect hydration of alkene. Indirect hydration of alkene. You have to remember reagents of it, and you have to remember this. Whenever an unsymmetrical alkene is there and you want to perform hydroboration oxidation reaction, I mean to say, if BH3 or B2H6 is there, this is the reagent due to which hydroboration takes place, and after that H2O2 OH negative, due to this oxidation will take place. Whenever you are having these types of reagents, you have to add water according to, or you have to add water across carbon-carbon double bond according to anti-Markovnikov's rule. That means if you are having carbon-carbon double bond with one carbon lesser number of hydrogen, another more number of hydrogens, then you use this one. But if you are having an alkene like this, say for example CH3, then CH, then double bond CH, then CH2, CH3, this is also an unsymmetrical alkene. But here carbon-carbon double bond is having same number of hydrogens, so you cannot use this trick. Then for this, you just remember, add water in such a way that negative part of water is added to that carbon of carbon-carbon double bond, to that carbon of carbon-carbon double bond, which is less sterically crowded, What is meant by that? That means this is having CH3, smaller alkyl group, but this carbon is having larger alkyl group. That means this is more crowded carbon, this is less crowded carbon. So major product will be, you have to break this pi bond, add OH here and add H here. I mean to say here, same reaction will give this product. CH3CHOH as major product, single bond CH2, single bond CH3. But here you can use this one, you can write down RCHOH and then CH3. I hope I am clear till now. I hope I'm clear till now. Let me know in the chats, am I clear till now? Because second concept is done and dusted. Second concept, we have completed the second concept. Now let me know in the chats. Let me know in the chats. Am I clear till now? This is the question in front of you. Let me know the answer of this question quickly in the chats. Let me know the answer of this question quickly in the chats. Oxymercuration, demercuration of 1-methyl cyclohexene. 1-methyl cyclohexene. It is like this. It is like this. So this is 1-methyl cyclohexene. You have to answer the question. You have to answer this question. You have to choose one option from these. Oxymercuration, demercuration of this gives. That means you have to add water to this. When you add water to this, because oxymercuration, demercuration means indirect hydration. So whenever you do oxymercuration, demercuration, you have to add water across carbon-carbon double bond according to Markovnikov's rule. That means you have to add OH over here and add H over here. So what is the name of this compound? What is the name of this compound? Choose the right answer from them. Let me know in the chats. What will be the answer? Exactly option number 1. Option number 1 is 1-methyl cyclohexanol. So this will be the right option among these 4. Great. Next is, which alkene on reaction with H2OH positive? That means it is classical carbocation mechanism. Gives a mixture of 2 isomeric alcohols. Remember, this is the mechanism. This is the mechanism. This is the mechanism. Have a look. So which type of alkene can form isomers if reaction takes place via classical carbocation? It is only what we call an unsymmetrical substrate. It is only an unsymmetrical substrate can result in the formation of isomeric products. But here product formation will be alcohol. That means isomeric alcohols will be formed from what we call unsymmetrical alkene. Is this clear? Is this clear? Let me know in the chats. Let me know in the chats quickly. So what will be the product over here? I mean, say, what will be the option over here? Option 1, exactly Gangadhar, exactly option 1 is the right answer. Exactly Chandani, exactly. This is very easy. Rufi, exactly. Nityasri, nice. Jaya, exactly. Great. Now, after this, we are having one more question. In the addition of bromine to ethene in CCl4. So first of all, remember this is X2. You have to add X2 to ethene. Ethene is this one. This is ethene. And we have to add bromine. But in CCl4 or in water, whatever. So whenever you add bromine to alkene in CCl4 or I mean say in water, because in water it will form HOBr. Then mechanism will be same, and mechanism is non-classical carbocation mechanism. And here we will result in the formation of this one. And what is this? This is cyclic bromonium ion, because in first step Br minus will be lost. And after that, in second step, Br minus will act as a nucleophile and that will attack from opposite side. That means anti-addition product will be formed. So, in the addition of bromine to ethene in CCl4, anti-addition occurs due to. Why anti-addition occurs? Because of formation of cyclic bromonium ion. Because of formation of cyclic bromonium ion. I mean, say here, it should be cyclic. It should be cyclic. So formation of cyclic mercurium ion, no. Formation of free radical, no. Formation of 4-membered transition state, no. So this is formation of cyclic bromonium ion. This is the right answer. After that, the reaction of C6H5CH, it's like this. Reaction is like this. This is C6H5CH double bond CH single bond CH3 with HBr. When reaction takes place with HF, HCl, HBr, HI, then reaction is an electrophilic addition reaction because it is taking place in absence of what we call peroxide. So what will be the product? Product will be simply like this. Major product will be simply like this. Br will be lost and we will get a resonance stabilized carbocation over here. So as this is the very stable carbocation, resonance stabilized carbocation, there will be no rearrangement. Hence, after this, bromine will attack to this carbocation and we will get this one. We will get this one. So which option is the right option? That means C6H5, CHBr, CH2, CH3. This will be the option, right option of this question. Exactly, 4 is the right answer. God bless you all. 4 is the right answer. Exactly, exactly, exactly. Now, after this, we are having this question. In reaction with HCl, an alkene reacts in accordance with the Markovnikov's rule to give a product 1-chloro, 1-methyl cyclohexane. That means it is like this. 1-methyl and 1-chloro. That means 1-chloro, 1-methyl cyclohexane. This is the product. Now let me know in the chats, this product is formed by the addition of HCl to this, or by addition of HCl to this, or addition of HCl to both, or addition of HCl to this. Let me know in the chats quickly. Let me know in the chats quickly what will be the answer. What will be the answer of this question? Quickly. Quickly. Ehsan, exactly. Rufi, exactly. Muhar. Okay, sorry, Rufi, you are not correct. Sorry. Exactly. Have a look. Safna. Yes, both 1 and 2. Both 1 and 2. Because here, when you add HCl, you have to add according to Markovnikov's rule. Negative part will go to this and positive part will go to this. So it becomes Cl, single bond CH3. That means the product is this. Similarly, negative part will go to this and positive part will go to this. So Cl and CH3 will be at the same position. So both 1 and 2 is the right answer. Exactly, option number 3 is the right answer. Option number 3 is the right answer. After this, we are having another concept, that is Markovnikov's and anti-Markovnikov's addition. Markovnikov's addition, we have already studied or discussed Markovnikov's addition. Now, here remaining will be this anti-Markovnikov's addition. Now, we will understand this anti-Markovnikov's addition. Anti-Markovnikov's addition. We will simply understand this Markovnikov's addition with the help of what we call Kharash's effect. With the help of Kharash's effect, or also known as peroxide effect. Peroxide effect. Have a look. What is this? This is simply addition of HBr to an unsymmetrical alkene. What is this reaction? Addition of HBr to an unsymmetrical alkene in presence of, peroxide. Say for example C6H5, C double bond O, C double bond O, C6H5. I mean to say peroxide. Now remember, if reaction is of unsymmetrical alkene and HF, HCl or HI with or without peroxide, reaction is electrophilic addition reaction, and intermediate at that time will be classical carbocation. But if HBr is added to unsymmetrical alkene in absence of peroxide, reaction is electrophilic addition reaction taking place via classical carbocation, and product will be Markovnikov's product. But whenever HBr is added to unsymmetrical alkane in presence of peroxide, product is anti-Markovnikov's product. What does that mean? That means negative part goes to that carbon which is having that carbon-carbon double bond which is having more number of hydrogens. So this will be our product. And remember, my dear lovely students, this reaction is an example of this reaction is an example of free radical addition reaction. This is an example of free radical addition reaction. And intermediate of this reaction is obviously free radical. So intermediate of this reaction is free radical. Now, have a look what is the mechanism of this reaction. Have a look what is the mechanism of this reaction. Have a look. First of all, initiation will take place, and that will be a step 1. And during initiation, what will happen? Have a look. Our peroxide, first of all, like say for example, if I am having a benzoyl peroxide, first of all, this peroxide linkage will break and it will result in the formation of a free radical, odd electron species. Odd electron species will be formed. Then this odd electron species, C6H5 double bond O radical, benzoyl peroxide radical. Now it will simply break this carbon-carbon bond and it will become O double bond C double bond O. That means it will become what we call carbon dioxide. It will become carbon dioxide and C6H5 radical will be formed. C6H5 radical and carbon dioxide will be formed. After that, this C6H5 radical will react with our reagent, that is HBr. Remember, if there is no peroxide, then there will be no formation of this radical, and if no radical is formed, then HBr will break like Br minus and H positive. But this radical will break this homolytically and will react with H, so it becomes C6H6 plus Br radical. So if Br radical is generated from our reagent, it's only because of peroxide. That is why this effect is known as peroxide effect. Now, have a look. As the radical has been formed from reagent, so this reaction is known as initiation. After that, step 2, I mean to say propagation will take place. Now, reaction will propagate. Reaction will propagate now. Have a look. Reaction will propagate now. In first step of propagation, a radical will attack. Radical will attack the substrate and will break this weaker pi bond and will result in the formation of C radical, C radical. This is primary carbon free radical. This is secondary carbon free radical. Have a look. Primary is less stable, secondary carbon free radical is more stable. Hence, as this is less stable, it is more reactive, so it will react with Br. It will react with Br. I will show like this. It will react with Br and it will result in the formation of a more stable carbon free radical. Now, let me know in the chats, why Br goes to this carbon, why not to this carbon? Because, let me know in the chats quickly, why Br goes to this carbon? Why not to this carbon? Why not to this carbon? Let me put on the lights first. Come on, my dear lovely students, come on, let me know quickly, Come on, let me know. Come on. Reason of anti-Markovnikov's addition is stability of carbon free radical. Because if Br is attached to this, then primary carbon free radical, less stable carbon free radical will be formed. So Br will go to this so that more stable carbon free radical will be formed. That means anti-addition is basically due to more stable carbon free radical. Now, second step will be the radical formed in first step will now react with another reagent, and this radical will break. I mean to say, now it will react with, not, this is not the reagent, HBr is the reagent. Now it will react with HBr, I mean say another molecule of reagent. Then what will happen? This radical will break this homolytically, and H radical and Br radical will be generated. H radical is more reactive than Br radical, so this radical will react with H, and it will result in the formation of CH3, CHH, CH2Br. That means anti-Markovnikov's product will be formed, plus Br radical will be generated. So our product, anti-Markovnikov product, is formed. Now the question is, why is it formed? Because Br goes to this position so as to form more stable carbon free radical. That means anti-Markovnikov's product formed during Karash effect, peroxide effect, or when HBr is added to unsymmetrical alkane in presence of HBr, is only and only because of formation of more stable carbon free radical. Now let me know in the chats, am I clear? Let me know in the chats, am I clear till now? Let me know in the chats, am I clear till now? Come on my dear students, because no one among you should be unable to solve your NEET examination or NEET organic chemistry paper. Come on. Okay, that's great. Now in final step, well, what will happen? In final step, these types of radicals will combine. So step third is termination. So product formation takes place in propagation, and all the steps of propagation must be exothermic. So our third step is termination. So what happens during termination? This radical, CH radical, CH2Br, it will react with another similar type of radical like this, CH3, CH radical, then CH2Br, and it will result in the formation of a product like this. CH3CH, here it is CH, here it is CH3. Then can I write down this CH2Br like this, CH2Br. Similarly here CH2Br. Both these will react, and this will be another product. Similarly, Br and Br. Have a look. This Br radical will react with another Br radical. That means Br2 can also be obtained during this reaction. Br2 can also be obtained. Now after that, this will react with this. I mean to say CH3CH radical, CH2Br will react with Br radical, and it will result in the formation of CH3, CHBr, then CH2Br. So in this way reaction will stop. Now let me know in the chats, am I clear till now? If I am clear, let me know the answer of this question. Let me know the answer of this question in the chats quickly. Let me know the answer of this question in the chats quickly. Come on, my dear students, let me know the answer of this question quickly. Come on, answer this question quickly. Answer, I'm waiting for the response. Come on. Asha, exactly. Chandani, exactly. Hema, exactly. Shafqat, exactly. Okay, that's great. So, as we know, this is anti-Markovnikov's addition of HBr to propene in presence of peroxide. Hence, radical is basically more stable radical which has to be formed, and we know it is basically a secondary radical because of which this anti-Markovnikov's product is formed. Hence, we will write down it's a secondary radical. After that, Which reagent gives anti-Markovnikov's addition of water to alkene? When you add water to alkene, which type of reagent or which reaction gives the product which is according to anti-addition of water molecule? Let me know quickly in the chats what will be the answer. Let me know quickly in the chats what will be the answer. No, Rufiz, and if you add HBr to peroxide, then it will be HBr added according to anti-Markovnikov's rule. But we have to add water. It's written over here, add water, not HBr. This is the option because we generally thought that it is anti-Markovnikov's addition, so write down HBr. No, it is anti-Markovnikov's addition of water. Come on. Exactly, it is 3, hydroboration oxidation. Exactly 3 is the right answer. Nithya, exactly, at the rate of shining, exactly. Okay. Great, Mithali Chaudhary, great. Nice. After that, we are having another reaction, that is aromatic electrophilic substitution reaction. Obviously, this is electrophilic substitution reaction of benzene. Now, have a look. Electrophilic substitution reactions are, I will write down like this, ESR, electrophilic substitution reaction of benzene or aromatic species. Remember, generally gets completed in 3 steps. We have to discuss mechanism of these reactions. Generally gets completed in 3 steps. Step 1 is always generation of electrophile. Step 2 is formation of a carbocation intermediate. And step 3 is aromatization. And remember, the most common electrophilic substitution reactions of benzene or aromatic species are halogenation, after that nitration, after that sulfonation, after that Friedel-Crafts alkylation, and Friedel-Crafts acylation. So these are the most common electrophilic substitution reactions of aromatic hydrocarbons. But remember, when aromatic hydrocarbon ring is attached to electron withdrawing group, or we can simply say when electron withdrawing groups are attached to, say benzene ring, that means they will withdraw electron from benzene ring, and that will deactivate that benzene ring towards electrophilic substitution reactions. And remember, such types of aromatic compounds to which electron withdrawing groups are attached generally do not show Friedel-Crafts alkylation or Friedel-Crafts acylation. That means limitation of Friedel-Crafts alkylation and Friedel-Crafts acylation is that aromatic compounds in which electron withdrawing groups are attached to aromatic ring, they do not show Friedel-Crafts reaction, whether it is alkylation or whether it is acylation. Now, we will have a look over halogen. We will discuss halogenation, nitration, sulfonation, Friedel-Crafts alkylation and acylation, but we have to first of all see what will be the electrophile of this and this reaction. Have a look. Now, let me write down over here a general mechanism of the reaction. So first step of this mechanism is generation of electrophile. So now it is first step, which means generation of electrophile. That means we have to generate an electrophile. The first step is generation of electrophile. First step is generation of electrophile. Have a look. These are very important reactions. These are very important reactions. Now, first, if I talk about halogenation, halogenation generally is either chlorination or bromination. Why? Because fluorination is violent, and iodination, when iodination takes place, it results in the formation of HI and reaction is reversible. So we will talk about either chlorination or bromination. Have a look. If I write like down this Cl2, this is chlorination, reagent of chlorination, and chlorination takes place or bromination takes place in presence of Lewis acid. Say for example, Lewis acid is this one. What will happen over here? These two will react together. These two will react together in this fashion. This will attack its electron to this, because this will act as a Lewis acid. It can accept electron pair, and then this bond will be broken. Hence, finally, we can say chloronium ion will be obtained as an electrophile if chlorination takes place. Bromonium ion will be an electrophile if bromination takes place. In nutshell, halonium ion will be the electrophile, and AlCl4 minus will be lost over here. So this is the electrophile of what we call halogenation, known as chlorination. After that, if I talk about nitration, remember what happens during nitration. Nitration generally takes place with the help of nitrating mixture. Nitrating mixture means HNO3 and H2SO4. Have a look. HNO3 and H2SO4 mixture is known as nitrating mixture. So this is H2SO4 and this is HNO3. During this, what will happen? This nitrating mixture reacts in such a way, that this OH will abstract H positive and this sulfuric acid will donate H positive. That means this will act as an acid and this will act here as a base. So during what we call this reaction nitration, HNO3 will act as concentrated HNO3 will act as a base because it abstracts H positive, donates its electron. So what will happen? It will result in the formation of H, O, S, double bond O, single bond O having a negative charge plus H, then O, then H having a positive charge over here, then it is NO2. Now, in second step, what will happen? This HOH, NO2, in this case, O becomes positively charged, so this is a good leaving group. It will leave and result in the formation of NO2 positive. Now after that, H2SO4, another molecule, we can say, will react. It will react with H2O formed in this. So this H2O will abstract H positive, will act as a base, and this is an acid, and it will result in the formation of H, O, S double bond O, O minus plus H3O positive. Have a look, my dear students. This is very important. Have a look how actually electrophile generates over here in second reaction known as nitration. This was halogenation, chlorination. This is nitration. Now, if I write down what we call a net reaction over here, can I say this is one H2SO4, this is another H2SO4? That means we have we have used two H2SO4 molecules on the reactant side. We have used HNO3 molecule on the reactant side. After that, this is the product, but this has been okay. This is the product. Okay, done. This is the product of this reaction, but it is used over here. That means I will not write down this one. This water is used over here, so I will not write down water neither on reactant side nor on product side. Can I write down this as HSO4 minus HSO4 minus? So it is twice HSO4 minus, or OSO3H minus twice. Then this and this will cancel out, this and this will cancel out, then it is NO2 positive and it will be H3O positive. So remember this is the electrophile of this reaction. So reaction, if reaction is halogenation, halonium ion is the electrophile. If it is chlorination, chloronium ion. If it is bromination, bromonium ion. And if nitration takes place with the help of, say nitrating mixture, nitronium ion is the electrophile of the reaction. After that, third reaction is sulfonation. HOSOOOH, that means H2SO4. It undergoes self-ionization like this. It will result in the formation of, have a look, it will result in the formation of this one. This will accept, one molecule will accept H positive, another will lose H positive. So it will result in the formation of, my dear students, it will result in the formation of H, O, S, double bond O, double bond O, then here it is O, then having a negative charge, plus this becomes H, O, H, with a positive charge on this oxygen, then S double bond O, then O, then H. Have a look. That HOH, as this is now a good leaving group because O is having positive charge, S double bond O, single bond O, single bond H. What will happen over here? This will leave and it will form a double bond over here. So what will be the, product over here? Product will be water plus, it is S double bond O, single bond, then it is double bond O, single bond H. This will, now this either this will act as an electrophile, or you can say that S double bond O, single bond H, it will react with H2O and H2O will abstract this H positive and it will result in the formation of SO3, S double bond O, plus what we call H3O positive. Remember, during sulfonation, either this is the electrophile or we can say this is the electrophile. But here, if I write down overall net reaction, then it is like this. One H2SO4, another H2SO4. That means twice H2SO4. It gives us what? This and this will be cancelled out over here. This will be cancelled out with that. This is HSO4 minus. Then it is H3O positive. And then it is SO3. O double bond S double bond S double bond O. That means it is basically SO3. And this SO3 can be an electrophile of the reaction. So you can say SO3 is an electrophile, or you can sometimes say that this is the electrophile. Why? Because this SO3 can react with H2SO4 and will result once again this one. So either this is the electrophile or SO3H positive is the electrophile of the reaction. After that, reaction number 4, Friedel-Crafts alkylation. What will happen over here? Either alkyl chloride will react with AlCl3, or it will react with, say FeCl3. Now, what will happen? Generally, it's alkyl chloride. It will react with this and this bond will be broken. Now, it will result in the formation of this one. Have a look. Carbocation is formed, so we have to rearrange if possible. Rearrange if stability of carbocation is increased. So, rearrange if possible. So this is an electrophile of this, reaction. This is an electrophile of this reaction. After that, we will be having another one, that is Friedel-Crafts acylation. Okay, but let me tell you, it can be either alkyl chloride or AlCl3. It can be alkene in presence of H positive, that can also act as an alkylating agent, or it can be an alcohol in presence of H positive, that can also result in the formation of R positive as an electrophile. Now it can be either acid chloride or acyl chloride, or you can use acid anhydride as well. So either acid anhydride or acyl chloride. Now, what will happen? This Cl will attack over this and this bond will be broken. Now, it will result in the formation of Rc positive double bond O. But here no rearrangement takes place as this is very stable. As this is very stable because of back bonding or resonance. So no rearrangement takes place over here. No rearrangement. So this is the carbocation where no rearrangement takes place. No rearrangement takes place. So this reaction, this reaction, this reaction, or these two reactions, these are the 5 reactions which you have to remember is that during halogenation it's halonium ion which acts as an electrophile. During nitration it's NO2 positive which acts as an electrophile. During sulfonation it's SO3 or SO3H positive which acts as an electrophile. After that it is simply what we call an alkyl chlorination, Friedel-Crafts alkylation. It is generally alkyl having a positive charge, alkyl carbocation acting as a electrophile. But here rearrangement can take place. In acylation, Friedel-Crafts acylation, it is what we call, acylium ion acts as an electrophile. Now, this was step number 1 of these 5 reactions. Now, what is step 2? Step 2 is formation of carbocation. We have to discuss mechanism over here. That's why I am showing all the mechanism over here. So, formation of carbocation. Formation of carbocation intermediate. Formation of carbocation intermediate. Have a look. Have a look. Have a look. Now, in first step, electrophile has been generated. Now that electrophile, I will write down E positive for that. That electrophile will attack now to the substrate. That means in our case, that will be an aromatic compound, say for example, benzene. Have a look, my dear students. Now, this E positive will react. What is this E positive? If chlorination takes place, then it will be Cl positive. If bromination takes place, it will be Br positive. If nitrogen has to take place, it will be NO2 positive. Otherwise, it can be SO3 or SO3H in case of sulfonation, or in case of Friedel-Crafts alkylation, it can be R positive, or in case of Friedel-Crafts acylation, it can be RCO positive. Now, what will happen over here? Here, this step is the slowest step of the reaction, hence rate determining step of the reaction. And it's a reversible step as well. Now, what will happen over here? In presence of this, it will attack. Electrophile will attack to this one and it will result in the formation of this. It can result in the formation of this. Here it's already H. Now electrophile will be added to this. Then here we know it will acquire a positive charge. As carbon forms a positive charge. Second thing, carbon forms a positive charge, so it's a carbocation intermediate. Second thing, from this to this, pi bond has been broken and new sigma bond is formed. And this carbon from sp2 to sp3 hybridization, from sp2 hybridized carbon, sp3 hybridized carbon has been obtained. This is also known as, if we draw its resonating structures like this, if we draw its resonating structures, have a look. If we draw its resonating structures, we can draw like this. We can draw like this. So this will be having a positive charge, then H and E. Similarly, this will resonate like this and it will form a resonating structure like this. Finally, can I form a hybrid like this? Can I form a hybrid like this? So hybrid is like this. This double bond is from either from this to this, and positive charge is also from this to this. This is known as what we call sigma complex. And this is known as actually the carbocation intermediate, or we can say rhenium ion, or we can say Wieland's intermediate. Wieland's intermediate. Why rhenium ion? Because it was arene, now it's a positively charged arene. Now this is rhenium ion. Have a look. Here pi bond is broken, sigma bond is formed. That's why sigma complex. Now let me show you further reaction. Now this is formed. As this is not stable, then in final step, what will happen? Aromatization takes place. So in final step, aromatization takes place. I mean to say, this structure, which is non-aromatic because of this sp3 hybridized carbon, it is converted to aromatic once again, like this. It will lose H as H positive from that position to which electrophile as E positive has been added or electrophile has been added. Now it will lose that H positive and it will form once again an aromatic compound. So what has happened over here? Hydrogen has been replaced by an electrophile. Now if this electrophile is halonium ion, then introduction of halogen is known as halogenation. If electrophile was, say NO2 positive, so here NO2 will be introduced in the ring, hence this will be known as nitration, or either it will be, say introduction of SO3H, sulfonation, it will be introduction of R, say alkylation, Friedel-Crafts alkylation, it can be introduction of this C double bond OR, say acyl, hence this can be Friedel-Crafts acylation as well. Now, here this H positive will be removed, basically the negative part. Which negative part? Either AlCl4 minus or this negative part HSO4 minus, or I mean to say this HSO4 minus or this AlCl4 minus. So either AlCl4 minus or HSO4 minus will abstract this hydrogen. So it can be either HSO4 minus or it can be AlCl4 minus in these reactions that will abstract this hydrogen. Either this will abstract or this will abstract this hydrogen. So any one among these will abstract hydrogen and it will result in the formation of Friedel-Crafts, what we call aromatic compound. Hence reaction is known as aromatization. Now have a look. So electrophile in case of benzene, if we are preparing electrophilic substitution reaction. If we are performing electrophilic substitution reaction, electrophile goes to benzene ring at any place. Why? Because electrophile goes to that position of aromatic ring which is having more electron density, and benzene is having electron density equally distributed at every carbon. So it will replace any hydrogen and it will be, electrophile will be introduced like this. But if we are having an atom or a group like this, if we are having an atom or a group which is having negative charge or lone pair of electron, remember such groups when such groups show resonance, they will donate electron towards the ring. That means they will show plus R effect. When they show plus R effect, they will simply increase electron density. They will increase electron density of the ring at ortho and para position. Ring at ortho and para positions. So such groups, remember, such groups are known as ortho para directing. And such groups are activating groups, except such groups are known as activating groups. That means activating groups are those groups which donate electron towards ring and increase electron density of the ring. Now, such groups are activating groups except halogens. What is meant by this point? It means halogens are ortho-para directing but deactivating groups. So remember, this is all because of resonance. So it's all because of resonance. Say such groups having negative charge or lone pair, when they show resonance, they become ortho-para directing, they become activating, except halogen. Halogens have lone pair, that means they will donate electron because of resonance, but they are not activating. They are ortho-para directing because of resonance, but they are deactivating because in case of halogen, minus I, electron withdrawing power is more as compared to plus R. yani electron donating power. That's why that overall halogens will deactivate, that halogens will simply reduce the electron density of the ring. That's why they are orthopara-directing, but they are deactivating groups. Remember this point. After this, you have to remember, this one. After this, you have to remember, if we are having an atom or a group such that this is having a vacant orbital, or polar pi bond, and shows resonance, then remember they show minus R, and remember they decrease electron density, of the ring at ortho and para positions, and hence such groups are known as meta directing groups and are deactivating groups. So those groups which show plus R are activating as well as orthopara directing except halogens, but those groups which show minus R, they decrease electron density at ortho and para position, hence they are meta directing and are deactivating groups. In addition to this, alkyl group, if attached to benzene, I mean to say, let me write down this in this fashion. If alkyl group is attached to benzene, remember this is simply orthopara directing. That means it increases electron density at ortho and para position and hence becomes orthopara directing, obviously with respect to electrophiles. Now, due to hyperconjugation or plus H. Similarly, if you are having CX3 group, it is meta directing. That means it decreases electron density by withdrawing electrons away from, I mean to say, this benzene ring and decreases electron density at ortho and para position. So this is meta directing due to reverse hyperconjugation or due to minus H. So these are few points which you must remember, you must know. After this, we are having a question like this: which of the following is the correct order of activating effect towards the electrophilic substitution? I will be waiting for the answer. Let me know in the chats quickly. What will be the answer? What will be the answer of this question? Let me know in the chats quickly. What will be the answer of this question? I am waiting, guys. Let me know in the chats quickly. What will be the answer of this question? Come on. Come on, guys. What will be the answer? Okay. The question is correct order of activating. Which groups are activating? Activating groups are, hence, have a look. Activating groups are those groups which are orthopara directing except halogens. That means these are activating groups. This is also activating group, but this is due to, because it's orthopara directing, but this is due to hyperconjugation. So, meta directing groups are deactivating groups, whether they are because of resonance or they are because of what we call hyperconjugation or reverse hyperconjugation. Now, let me know in the chats. You have to tell me activating groups. Strong activating group is that which donates electron towards ring more strongly. Do you know resonance is powerful than hyperconjugation? Now, it will show nitrogen, NH2 will show plus R. This will show also plus R, but plus R of NH2 is more. So NH2 first, after that it will be O, it will be OCH3, both shows plus R, but it shows more stronger plus R, then it will show plus H. But here we know this Cl is deactivating because its minus I is stronger than its plus R. So that's why this will be the option. This is the option of our question. Now, after that, in Friedel-Crafts alkylation, benzene is treated with CH3, CH2, CH2, Cl. Now let me know, this is Friedel-Crafts alkylation. What will happen? This will react with this and it will leave as Cl, AlCl4 minus. Then we will get CH3, CH2. Can I write CH2 like this? Then CH2 positive. Now this is the carbocation. Hence we will simply shift hydride. So 1,2 hydride shift takes place, so rearrangement takes place, so that it can result in the formation of more stable carbon free carbocation. This is 6 hydrogen here, so 6 alpha hydrogen. This is stable because of 6 alpha hydrogen. This is stable because of 2 alpha hydrogen. So this is more stable carbocation. So first alkyl carbocation is formed, then rearrange if possible. So there is possibility of rearrangement because it results in the formation of more stable carbocation. Then it will be directly added to benzene. That means product, when treated with benzene, product will be like this: isopropyl benzene, cumene. Isopropyl benzene will be the product, or cumene will be the product. Now, which one is isopropyl benzene? That means C6H5 CH and CH3 CH3. That means this is the right answer. This is the right answer. After that, during bromination of nitrobenzene, nitrobenzene is this one. During bromination of nitrobenzene, nitrobenzene is this one. This is nitrobenzene, and this is a group which shows minus R. That means it will withdraw electron. It will withdraw. It will simply withdraw electron away from benzene ring, away from benzene ring, and will decrease electron density at ortho and para. Electron density at ortho and para positions. When it decreases electron density, that means it's a deactivating group. So when ring is deactivated, electron density of ring is decreased. That means electrophilic substitution generally does not take place. But if it takes place, then it's bromination. Then Br positive will go. But where? As ortho and para position has been, electron density of ortho and para has been decreased. Hence, can I say such group is meta-directing. That means it will direct electrophile towards meta position. So it will be meta bromo nitrobenzene. It can neither be ortho bromo nitrobenzene nor para bromo nitrobenzene. It will be simply meta bromo nitrobenzene. Let me know in the chats, am I clear till now? So that we will discuss another concept, that is SN1 and SN2. Let me know clearly. Let me know quickly. Let me know quickly in the chats. Let me know in the chats. Am I clear till now? Am I clear till now, my dear lovely students? Let me know quickly. Let me know quickly. Let me know quickly. Okay, that's great. Chandani, thank you. John Steven, thank you. Kanmani, thank you. Okay. We will stop at 12. We will be having 3-hour session today. We will discuss other concepts in another session, which is on Sunday at 8. Okay. Now have a look. Now we will be having SN1 and SN2 reaction. Now first of all, what is SN1 reaction? You must know what is meant by SN1 reaction. SN1 is substitution nucleophilic unimolecular or unimolecular nucleophilic substitution reaction. It is that nucleophilic substitution reaction for which rate is directly proportional to molar concentration of substrate. Remember these points. Remember these points. This is point number 1. After that, you can write down rate is equal to some constant K, that's rate constant or velocity coefficient or specific reaction rate. Now, this is the point number 1. Point number 2 is, from this rate law equation or from this rate is directly proportional to molar concentration of substrate, from these 2 points, it's clear that SN1 is unimolecular. SN1 is unimolecular reaction and SN1 is a first order reaction. It's a first order reaction. After that, remember SN1 reaction is a multi-step reaction. That means it gets completed in more than one step, generally in 2 steps. It's a multi-step reaction. After that, have a look, my dear students. After that, step 1, remember, step 1 is ionization step or formation of carbocation and is the RDS of the reaction and is the slowest step of the reaction, hence RDS of the reaction. Then few more points you must know. After that, intermediate is carbocation. Hence rearrangement can be possible. Remember dear students. After that, step 2 is attack of nucleophile. One more point you must know is, if solvent acts as a nucleophile, then SN1 is called solvolysis. Now, remember that rate of SN1 is directly proportional to stability of carbocation formed in RDS. Very important point. We are not discussing, SN1, because we have to only differentiate SN1 and SN2. We must know few points about SN1 and SN2 so that we can solve the questions of SN1 and SN2. After that, remember, rate of SN1 is directly proportional to leaving ability of the group. And rate of SN1 is directly proportional to dielectric constant value of the solvent. Listen carefully, my dear students. Whenever you are having an alkyl halide, you have to break CX bond, you have to form a carbocation. Alkyl halide which can form more stable carbocation shows SN1 faster. Similarly, among alkyl halide, I minus is a better leaving group, after that Br minus, after that Cl minus, after that F minus. That means if we are having alkyl iodide, alkyl bromide, alkyl chloride, alkyl fluoride will show faster reaction because iodide is a better leaving group, after that RBr, after that RCl, after that RF. Similarly, Solvents having high dielectric constant value can show faster SN1. And remember forever, generally polar protic solvents like water, alcohol, carboxylic acids, etc. I mean, say polar protic solvents have generally high dielectric constant value. Hence, such solvents favor SN1 reaction. So, this is all about SN1. Now, after that, let me tell you about SN2. Or I can add few more points like stereochemistry. During SN1, remember, partial racemization takes place. Partial racemization takes place. Partial racemization takes place. Due to more inversion or backside attack of nucleophile on carbocation, then retention means then front side attack of nucleophile on carbocation, then retention due to why this has happened. It happens due to intimate ion pair formation. Due to intimate ion pair formation. So remember these points because you have already studied these. Now you have to revise these points so that these points will help to solve the question. After this, if we talk about SN2 is bimolecular nucleophilic substitution or substitution nucleophilic bimolecular. For this, rate is directly proportional to molar concentration of substrate and molar concentration of nucleophile. So we can say R is equal to constant K into molar concentration of substrate and molar concentration of nucleophile. Hence, we can simply say that SN2 reaction is a second order reaction and a bimolecular reaction. So SN2 is a bimolecular reaction and a second order reaction. It's a bimolecular reaction and it's a second order reaction. SN2 is a second order reaction. It's a second order reaction. After that, SN2 is a single step reaction. Remember these points, I will show example as well. So it's single step reaction. It's single step reaction. Then SN2 is a concerted reaction. Is a concerted reaction. Concerted means formation of a bond and breaking of bond takes place simultaneously. So it's a concerted reaction or it is a concerted mechanism. After that, remember here rate, I mean to say, we can simply say no intermediate carbocation is formed. No intermediate carbocation is formed during this reaction. Hence no rearrangement. Hence no rearrangement takes place. Hence no rearrangement takes place during this reaction. Reaction is believed. SN2 is believed to occur via a transition state. Now after that, remember, rate of SN2 is directly proportional to stability of transition state. Directly proportional to stability of transition state. Rate of SN2 is directly proportional to leaving ability of the group. That means once again, in Ri it will be fast as compared to RBr, as compared to RCl, as compared to RF. So directly proportional to leaving ability of the group. And remember, polar aprotic solvents like dimethyl formamide, dimethyl sulfoxide, acetone, hexamethyl phosphoramide, hexamethyl phosphoramide, etc. Favor SN2 reaction. Favor SN2 reaction. And rate of SN2 reaction is inversely proportional to steric crowding. Steric crowding at alpha or beta positions with respect to electrophile. I mean say, if leaving group is attached to a carbon known as alpha carbon, if to that carbon alkyl groups are attached, many alkyl groups are attached, so it becomes sterically crowded, so nucleophile will not attack at that time at alpha position, so there will be no SN2 or rate of SN2 will be less. Similarly, if crowding or alkyl groups at beta position with respect to leaving group will be increased, rate of SN2 will be decreased. Now, after that, remember stereochemistry, that is during SN2 reaction, 100% inversion, that means backside attack of nucleophile takes place. 100% inversion called Walden inversion takes place. Walden inversion takes place. So here 100% inversion takes place. But in SN1, partial racemization takes place. More inversion as compared to retention takes place. So Walden inversion takes place. Now, have a look towards an example. Have a look. Have a look, my dear students. Have a look. Suppose we are having CBr and here it is pH. Here it is, say for example, ethyl, and here it is, let us suppose, methyl. That means this carbon is sp3 hybridized carbon and this is a chiral center because it's sp3 and is attached to 4 different groups. So this is what we call a chiral center. Now, when it is treated with water, I mean to say, if it is taken in polar protic solvent, for example water, what will happen? This polar protic solvent will help in, I mean to say, cleavage of this CX bond, and it will result in the formation of C with a positive charge and Br with a negative charge, and its pH, ethyl and methyl groups are like this. Now, here remember ion formation takes place because C and Br bond has been broken, but this ion pair is not solvated, I mean say this is not solvent separated ion pair. That means in start, this, I mean say solvent molecules are not, I mean say surrounding this Br minus or C positive. Those solvent molecules will surround these ions after some time, and these ions will be separated, and that at that time ion pair will be known as solvent separated ion pair. But this is not solvent separated ion pair, this is known as intimate ion pair. This is known as intimate ion pair, or this is known as contact ion pair, or this is known as what we call tight ion pair. Now, what will happen? After this, nucleophile will come and it will attack. Suppose our solvent acts as a nucleophile. Then this is a neutral nucleophile. Whenever it attacks, it acquires a positive charge. Finally, it will lose H positive. So let me remove H positive first. But actually, H positive is removed after the attack. Now, for the sake of simplicity, let us remove H positive. Now, this nucleophile will attack carbocation either from that side from which leaving group leaves, that side is known as front side, or from the side opposite to the side from which leaving group leaves, that is known as back side. Now, let me know in the chats, can this water or nucleophile attack on carbocation from the front side? Answer is no. Why? Because the electron cloud of this nucleophile and electron cloud of this Br minus or leaving group will repel each other. So what will happen? It will attack from backside. Its hybridization is sp2. Now it will attack from backside. When it attacks from backside, that means OH will form a bond with this carbon, and this carbon once again forms 4 bonds. That means it becomes sp3. So the product of reaction will be like this. It will be like this. As it's a tetrahedral structure, so I will write down Et and Me in this fashion. Once again, it is sp3 hybridized carbon and a chiral center. Now, you know this is having priority number 1, priority 2, priority 3 and priority 4. Least priority or fourth priority is on dash. So 1, 2 and 3. Its configuration around chiral center here is S. But here, configuration around chiral center will be R. That means configuration of chiral center has been changed from S to R. So backside attack, due to backside attack, configuration has been changed. So we call this as inversion product. Backside attack results in the formation of inversion product. Now, first of all, only inversion will take place. After some time, water or solvent will separate these ion pairs. So these ion pairs will become solvent separated ion pair. That means at that time, now nucleophile will come and it will attack on this carbocation from this side, because this Br minus has been separated by solvent. So after some time, it will attack on front side as well as on back side. That means after some time, this is initially. After some times, can I say after some times, this product as well as this product, both will be formed. Have a look. Both will be formed. And we know this is a chiral center. We know this is having 1, 2, 3 and 4. I mean, say this is having configuration R. And this is having 1, 2, 3 and 4 configuration S. So from S to R, that means it is inversion. Now from S to S, this is what we call retention. Now tell me, my dear lovely students, can I say due to intimate ion pair formation, first only inversion takes place. After some time, when this ion pair becomes solvent separated, then inversion as well as retention takes place. But here inversion as well as retention takes place. That means both these enantiomers will be formed. So can I say racemic mixture has been obtained? Racemic mixture has been obtained means racemization takes place. Hence, we can say during SN1, racemization takes place. But the question is, can I say first inversion forms, after that inversion forms. So inversion will be more, backside attack will be more as compared to retention. Suppose it is 2%, then both will be 98%. That means 49 and 49. So 2 plus 49 will be 51% and this will be 49. In nutshell, can I say backside attack is more? If backside as well as front side both are 50%, 50%, we call that racemization as complete racemization or 100% racemization. But here racemization will not be 100% because inversion is greater as compared to retention. Suppose inversion is 51%, retention is 49%. That means racemization will be 49 and 49, only 98%. So that's why I have written over here in SN1 reaction that partial racemization takes place. That means racemization is less than 100% because due to more inversion than retention, due to intimate ion pair formation. Yeah, as a result of intimate ion pair formation. I hope this is clear what is known as SN1. So this is stereochemistry of SN1 reaction. Now, this is the rate determining step. So that solvent which has high dielectric constant value, that means solvent which has high tendency to separate this CX bond will favor SN1, and Those solvents which have high dielectric constant values are polar protic solvents. That's why polar protic solvent favor SN1 reaction. Second, more better the leaving group is, more formation of carbocation will take place and SN1 will be fast. And we know IClBrF or IBrClF, I minus is better leaving group, then Br minus, then Cl, then F. That's why Ri, Rbr, Rcl, Rf will be the reactivity order. After that, if substrate forms a carbocation, more stable the carbocation, more faster will be the rate of SN1. So this was all about SN1. After that, if we talk about SN2, reaction. Now, what will happen in SN2? Have a look. SN2 reaction, say for example, suppose we are having an example like this. And let us suppose this is a halogen, say for example I or Br, whatever. So this is sp3 hybridized carbon and a chiral center. This is 1, this is 2, this is 3, this is 4. If we see the configuration here is S. If we use nucleophile, have a look. A stronger nucleophile will attack electron deficient carbon, but it will not attack from the front side because because here bromine is present with electron cloud. So it cannot attack from the front side because there will be steric repulsion between electron cloud of bromine and electron cloud of nucleophile. So there will be steric repulsion. So nucleophile cannot attack front side. This is the one reason written in NCERT. Another reason is like this. We know this is a sigma bond. So this is sigma bonding molecular orbital will be here, which contains 2 electrons. But anti-bonding sigma orbital or sigma star will be opposite, exactly opposite to that of this sigma bonding molecular orbital. That means it will be like this. This is, I mean to say, sigma star or sigma anti-bonding molecular orbital. Now, can I say it's opposite to that of bonding molecular orbital and it is empty? It is empty. Now, as it is empty, nucleophile will try to give its electron to empty orbital. That's why it will attack this electron deficient side from backside. Now, when it attacks this from backside, this bond will be broken. So, formation of this bond and breaking of this bond takes place simultaneously. That's why this is known as a concerted mechanism or single step mechanism. So, this step is slowest step of the reaction and rate determining step of the reaction. And this reaction is believed to occur via a transition state. So, these 3 bonds, I will show these 3 bonds like this. CH3, D and H. Now, this bond starts breaking. So, Br will be having a slight negative charge. This bond starts forming and I will say this will be having slight negative charge. So, this is the transition state. Carbon of the transition state, which involves basically this nucleophilic substitution, remember, is sp2 hybridized and it is penta-coordinated. 3 bonds are normal single bonds and 2 are partial single bonds, and its geometry is trigonal bipyramidal. So it's having trigonal bipyramidal geometry, but as we know transition state is highly unstable, then it will simply lose, I mean to say it will lose now this leaving group will be lost and reaction is very fast, and after that product will be over here. So product will be like this. Once again an sp3 hybridized carbon or center is there. After that it will be D and it will be H. Now have a look. This is 1 because this is a chiral center. This is 2, this is 3 and this is 4. So what will be the configuration? Configuration will be R. So remember, if a reaction takes place at chiral center, if SN2 reaction takes place at chiral center, its configuration will be changed. That means inversion takes place, and that 200% inversion takes place. Only backside attack takes place because front side attack cannot take place because it cannot give electron from this side as its anti-bonding molecular orbital is empty from opposite to that of leaving group. That's why it attacks from backside. Now the question is, if I will replace this D and H with alkyl groups, So more number of alkyl groups at alpha position, more hindrance this nucleophile will feel. So attack of nucleophile will become difficult. That's why if steric crowding at alpha or beta position increases, rate of SN2 will decrease. Similarly, more stable the transition state, more faster will be the reaction. More better the leaving group, more faster will be the reaction. More stronger the nucleophile, more faster will be the reaction. More concentration this nucleophile will be having, more, faster will be the reaction. So this was all about SN1 and SN2. After that, we will be having few questions over here. Now, let me know, my dear lovely students, let me know the answer of this question. Come on, dear students, let me know the answer. Come on, I will be waiting for you. Answer this question. Very, very, very easy. This question is very, 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 very easy. Come on, you just answer the question. Exactly. 4 is the right answer. Because during SN1, it is partial racemization. After this, consider the reaction, and this reaction will be fastest in. These are basically the solvents. These three are polar protic solvents. This is polar aprotic solvent. Remember, polar protic solvents favor SN1 and polar aprotic solvents favor SN2. So for that, you must know this is a primary alkyl halide. Remember, let me write down over here. If we are having primary methyl primary halide, then secondary alkyl halide and a tertiary alkyl halide. Remember, SN1, SN2. It will never show SN1, it will always show SN2. It will not show SN1, it will show SN2 except this one. Except this one. This is known as neopentyl halide. Neopentyl halide shows SN1, it will not show SN2 because of steric crowding at beta position. Okay. It will be shown both. Secondary alkyl halide will show SN1 as well as SN2. Tertiary will not show, SN2, it will show SN1. So this is clear. Now, the only thing is that secondary can show SN1 as well as SN2. Now, secondary will show SN1 if nucleophile is weak. Neutral nucleophiles, weak nucleophiles, then SN1. Negatively charged nucleophiles, stronger nucleophiles, SN2. And after that, remember, there are few compounds like this, in which pi bond is present at alpha position, like this, or in which leaving group is present at bridgehead position. These neither show SN1 nor they will show SN2. Remember, similarly, if you are having this one, in which halogen is attached to alpha position and there is a pi bond at beta position, say allyl halide or benzyl halide, or in which alpha position is having an atom containing lone pair of electron. These generally show, these can show SN1 as well as SN2, but they will prefer SN1. So you have to remember these as well. Okay, now come on. This is Na positive Cn minus. This is 1 degree alkyl halide. 1 degree alkyl halide generally prefers SN2. And second thing, this is a stronger nucleophile. It simply attacks over here and Br will be lost. So this will be the product. So as this is an SN2 reaction, it will be favored by polar aprotic solvents. After that, arrange the following compounds in order of reactivity towards SN1. What we have to do is break this bond, form a carbocation, break this bond, form a carbocation, break this bond, form a carbocation. Have a look, this carbocation is back bonding stabilized. So this is more stable as compared to this. Secondary carbocation, primary carbocation. Secondary are more stable, but among these two, back bonding is more stable as compared to hyperconjugation or inductive effect. So it will be C, then B, then A. First of all, it will be C, then it will be B, then it will be A, because we are having SN1 reaction. After that, rate of SN1 is directly proportional to stability of carbocation. So form the carbocation and you can answer the rate of the reaction. Okay, match the alkyl halides. Match the alkyl halides with the predominant mechanism when treated with OH minus in water. Okay, when you use OH minus in water, that means you are using a stronger nucleophile. Okay, with methyl and 1 degree, they will always show, have a look, methyl and 1 degree, they will always show SN2. So methyl will show SN2, this will show SN2, but here at alpha there is no alkyl group or crowding, but at this there will be one alkyl group. So here little bit crowding will be there. So both will show SN2, but this will show faster SN2, this will show slower SN2. So fast SN2, that means P gives 4, that means this will be the answer, because another will be having 2, 3, 2, but still P gives 4 or P and 4, match these two, then this will show SN2 but slower than this one, that means S will be 3, S3, yes. Okay, now this is secondary, this is primary. Primary will always show this is tertiary. Tertiary will always show SN1, R will show 2, that means this one. Then this is secondary. Secondary in presence of stronger nucleophile show SN2 but slow, then it will be SN2 like this. So this is the answer. So my dear lovely students, I hope everything is clear till now. Am I clear till now? Let me know in the chats quickly. What do you want now? Come on, let me know in the chats. Do you want me to discuss one more concept, or should we stop over here and we'll continue the same on Sunday at 8 p.m. Let me know in the chats quickly. Should we stop or should we continue? Come on, let me know. One more. Chandini is saying one more. Asiba is saying Sunday. Okay. Yes, sir. Let's discuss one more. Rufiz. Now, Azmat Khan. Okay. Come on. Let me one more. So, I will go with majority. So, there will be one more. Now, another is dehydration of alcohols. But let me tell you, this is intramolecular dehydration, which we will be discussing. Intramolecular dehydration. In acidic medium. Have a look. If we will be having an alcohol like this, our reaction is with H positive, and this H positive is actually H3PO4 or H2SO4. So this came from either H2SO4 concentrated or H3PO4 concentrated, and we will simply heat. Now, what will happen? What is the mechanism over here? Have a look. Its mechanism is very important. Very important. First of all, We know OH is not a leaving group or it's not a good leaving group. So OH is not a leaving group, or we can say OH is not a good leaving group. It will react with H positive first. So when it reacts with H positive, that means with acid, it will result in the formation of CH3, C, CH3, then CH3, then OH and H with a positive charge. Now, this is a poor leaving group, or it's not a good leaving group. This is a very good leaving group. Now, this leaving group will leave and it will result in the formation of a carbocation. This step is the slowest step and hence rate determining step of the reaction. So it will result in the formation of a carbocation like this. Now remember, as carbocation is formed, wherever carbocation is formed, we have to check whether rearrangement takes place or not. Now we know in this case there will be no rearrangement. Then what will happen over here? This carbocation will lose now hydrogen from the position adjacent to the carbocation. From the position adjacent to the carbocation in this fashion. So either from this position or from this, H positive will be lost. That means this H positive acts as a catalyst. First, protonation of alcohol takes place and results in the formation of, this one, oxonium ion or protonated alcohol. Then water will be lost. Then carbocation is formed. After that, deprotonation takes place and we will get an alkene. We will get an alkene over here. So this reaction is actually elimination reaction taking place via formation of carbocation. So we can simply say this is an example of E1 reaction, unimolecular nucleophilic substitution reaction. And rate of this dehydration. Rate of this dehydration is dependent on stability of carbocation. Say for example, if we are having an alcohol like this, and if we are having an alcohol like this, suppose we have to find out the rate of dehydration. What will we do? We will simply remove this. This is the trick. Actually, it reacts with H positive of acid, becomes OH2 positive, then water will be lost and a carbocation will be formed. Similarly, form a carbocation over here. We know this carbocation is stabilized because of hyperconjugation. This is stabilized by resonance. But here resonance is more. That means this is most stable carbocation. As this is most stable carbocation, rate of dehydration will be simply like this. So rate of dehydration of this will be simply 2 greater than 1 greater than 3. So more stable the carbocation formed after removal of OH, more will be, dehydration of that alcohol. I hope this is clear. Let me know in the chats, is this clear or not? Now, here, which alcohol gives the most stable alkene upon dehydration? Which alcohol gives the most stable alkene upon, dehydration? So, you have to dehydrate them. If you remove OH from this position and H from this position, alkene formed will be this. Here, alkene formed will be like this. This is actually CH3, so it becomes CH2, double bond CH, and then it's once again CH3. Here it is CH2, double bond C, single bond CH3, single bond CH3. Then here it will be CH3, single bond CH, double bond CH2. So these are the alkenes. Have a look. In this, there is no alpha hydrogen. In this, there is, 3 alpha hydrogens. Then here, alpha hydrogens are 6. Here, once again, 3 alpha hydrogens are obtained. That means these two are same. So which alcohol gives most stable alkene? This gives most stable alkene. So this is the product of the reaction. I mean, say this is the answer of this question. After that, dehydration of cyclopentanol. Cyclopentanol is this one, my dear students. Cyclopentanol is this one. What will happen? It will lose, I mean, say this, on treatment with H positive. So first, it will simply first reacts with H positive. When it reacts with H positive, what will happen? What will happen? It will result in the formation of OH with a positive charge. Then this water will be lost. Water will be lost. When water is lost, it results in the formation of a carbocation. After that, H will be lost as H positive from the position adjacent to the carbocation, either from this position or from this position. Say for example from this position, then it will result in the formation of cyclopentene. So this is the cyclopentene, first option. This is cyclopentanone, no. This is cyclopentane, no. This is cyclohexene, no. So cyclopentene will be the product. I mean, say will be the option. Which of the following is not the product of dehydration? Have a look. When it reacts with H positive, what will happen over here? This will attack over here and it will result in the formation of this one, OH2 with a positive charge, then like this. After that, this water will be lost and it will result in the formation of, have a look, my dear lovely students, have a look. It will result in the formation of a positive charge over here. Yes or no? So positive charge, carbocation will be formed. But this carbocation is already 3, 5 and 6. 6 alpha hydrogens are there. So this is already very stable carbocation. There will be no further, I mean to say, rearrangement. Then carbocation is this. So hydrogen will be lost either from this. When hydrogen will be lost from this position, double bond will be over here. Double bond will be over here. That means this will be the product. If hydrogen will be lost from this alpha position, double bond will be over here. That means double bond will be over here. This one. If this hydrogen loses hydrogen, if this alpha position loses hydrogen, double bond will be over here. That means this is possible, this is possible, this is possible, this is not possible. So this is our option. This will be our option. Then here this is very, very small, I mean say concept. So let us finish this concept and after that we will stop today's session. Now this is distinction between 1 degree, 2 degree and 3 degree alcohols. First is by Lucas test. Have a look, my dear students. If we are having primary alcohol, primary alcohol on treatment with Lucas reagent is HCl and anhydrous zinc chloride. This is Lucas reagent. At room temperature, no product formation takes place, hence no turbidity appears. But let me tell you, my dear students, if we slightly increase the temperature, reaction takes place. That means turbidity can appear after heating. After heating, this reaction will be formed. Alkyl chloride will be formed, OH will be lost and Cl, OH will replace, this OH will be replaced by Cl. That means alkyl chloride will be formed, turbidity can appear, but after heating, not at room temperature. Secondary alcohol reacts with Lucas reagent and can form what we call a secondary alkyl chloride. That means turbidity appears. But this turbidity appears after 5 to 10 minutes. Remember, if we are having a tertiary alcohol and we treat Lucas reagent with tertiary alcohol at room temperature, tertiary alkyl chloride will be formed very immediately, very fast. That means immediate turbidity appears. That means actually this Lucas reagent can be used to distinguish 1 degree, 2 degree, 3 degree alcohol. That's why this is known as Lucas test. Say for example, if we want to see whether this test tube contains 1 degree, say 2 degree or 3 degree alcohol, we will add, at room temperature, we will add Lucas reagent. If turbidity appears immediately, it is 3 degree. If turbidity does not appear, it appears after heating, then it is primary alcohol. If it appears after 5 to 10 minutes, then it is secondary alcohol. So can I say from this, turbidity, basically appearance of turbidity is actually directly proportional to stability of carbocation. More stable the carbocation is, because 1 degree, 2 degree and 3 degree, among 1 degree, 2 degree and 3 degree alcohol, which can form more stable carbocation after removal of OH, obviously 3 degree. So more stable the carbocation, more faster will be the appearance of turbidity. If this turbidity appears in seconds, that means this is all because of, say, carbocation formation. So that species which cannot form carbocation will not simply show appearance or will not show what we call turbidity. Now, after that, and another test is Victor-Meyer's test. Victor-Meyer's test. So with the help of this test, we can also distinguish 1 degree, 2 degree and 3 degree alcohol. Have a look, my dear lovely students. Have a look. With the help of this test, we can distinguish 1 degree, 2 degree and 3 degree. And this is also known as RBC test. What you have to remember is, first of all, if we have alcohol, whether it is 1 degree, whether it is 2 degree, whether it is 3 degree, which is present in a test tube, and we have a doubt whether it is 1 degree, 2 degree or 3 degree, we don't know whether it is 1 degree, 2 degree or 3 degree. We want to know whether it is 1 degree or 2 degree or 3 degree. So 1 degree, 2 degree, 3 degree alcohol is there. What we have to do is, we will add either iodine in presence of red phosphorus. What will this iodine in presence of red phosphorus reacts? How will it react with alcohol? It will simply replace OH and I will be there. That means when it replaces OH and I comes in place of, say, alkyl, this alcohol OH, in place of OH, alkyl iodide will be formed. That means you can take all those reagents which can replace OH by I. That means you can also use what we call HI. You can also use, say, those reagents in which OH will be replaced by I. So first of all, you can use this. After that, you have to use AgNO2. So the alkyl iodide formed, Ag will replace that, will react with I and AgI will be precipitated, and that I will be replaced by nitro. So nitroalkane will be formed. After that, we will add HNO2. If tertiary alcohol is there, HNO2 will not react. So nitroalkane will be there. So solution will be colorless. But if secondary alcohol is there, this HNO2 will react with that nitroalkane and it will result in the formation of pseudonitrile, and that is blue in color. But if 1 degree, alcohol is there, it will react with that 1 degree alcohol because at that time nitroalkane will be formed from 1 degree alcohol. It will react with that nitroalkane and it will result in the formation of nitrolic acid. After that, we have to add NaOH. Finally, this tertiary will not react with this, so it will be a colorless. Similarly, secondary alcohol, secondary alcohol has given, pseudo nitrile to this. This cannot react with pseudonitrile, so it remains as blue color, but it can react with nitrolic acid, so it results in the formation of red color. I mean to say, if we are having red color or blood red color, red color or blood red color appearance takes place after these, then remember it is 1 degree alcohol. Then it is 1 degree alcohol. If blue color appearance takes place, if appearance is blue in color, then it is 2 degree alcohol. And if it is colorless, remember, then it is 3 degree alcohol. Then it is, 3 degree alcohol. So it is R, B and C, red, blue and colorless. So this is what we call Victor-Meyer's test. Have a look towards its question. Given below are two statements. Statement 1. In Lucas test, primary, secondary and tertiary alcohols are distinguished. Yes, on the basis of their reactivity with concentrated HCl and ZnCl2 known as Lucas reagent. Exactly correct statement. Exactly correct statement. Now, let me know in the chats, is statement second true or false? Primary alcohols are most reactive. Primary alcohols are most reactive. Let me know quickly. Is this true or false? Statement first is true. Statement first is true. What about statement second? What about statement second? What about statement second? Come on, let me know. Is statement second true? Pujari, no. Exactly. Statement second is incorrect. Exactly. So what will be the answer? What will be the answer? What will be the answer? Statement 1 is correct, but statement second is incorrect. So this will be our answer. After that, which alcohol gives red color? Which alcohol gives red color on, say Victor Meyer's test? Which alcohol gives red color during Victor Meyer's test? Is it primary? Is it secondary or tertiary? Is it primary, secondary or tertiary? Is it primary, secondary or tertiary? This is butanol. This is butanol. That means this is primary. This is butanol, which means it is secondary. This is secondary or butanol. This is 2-methyl and 2-ol, say 2-methyl propanduol. This is tertiary. And this is cyclohexanol. This is secondary. So this is secondary, this is tertiary, this is secondary, this is primary. Let me know in the chats. Let me know in the chats. Which gives red color with Victor Meyer's test? Exactly, it's 1 degree. After that, a compound does not react with Lucas reagent. Even after heating, it does not react with Lucas reagent. Even after heating, this is very important point. Because 1 degree alcohol does not give, say turbidity, but at room temperature. But if it is heated, on heating, it gives, say turbidity. So 1 degree alcohol is not the answer. 2 degree alcohol is not the answer because it can form turbidity even at room temperature. 3 degree is not the answer because it forms turbidity immediately. So the answer is phenol. Why is it so? Have a look. Because for turbidity to appear, we have to break CO bond, but here we cannot break CO bond because this CO bond is strong bond because of partial double bond character as a result of resonance. So it cannot form a carbocation at all. Or even if we break this bond, then carbocation formed is highly unstable. It's unstable carbocation. So whenever carbocation is unstable or we cannot break CO bond, then remember it will never give what we call test with Lucas reagent, or it will not form turbidity with Lucas reagent. So this will be our product. This will be our product. After this, this will be our last question of today's session. Come on, let me know quickly. Victor Meyer's test for alcohols involves all except treatment with HI. This is correct. Then after that, either I2 red phosphorus or HI. Then AgNO2. This is also correct. HNO2. This is also correct. After that, it must be NaOH. But here it is CuO. Now let me know which one is incorrect, because here question is Victor Meyer's test for alcohol involves all except. So except what? Except what? Which option? Exactly option number 4. So my dear lovely students, I am really thankful to all of you. So it's a big thank you for you all. And I wish that you all goes to your favorite GMCs. So I hope you enjoyed the session. After ending this live stream, I would want you all to comment that how much you like today's session, but in comment section, not now, not now. Thank you, thank you. Thank you everyone. Thank you Asiba. Thank you Vishnavi. Thank you Bhargav. Thank you Gauri. Thank you Baswat. Thank you Raman. Azmat, thank you. Thank you Chana. Yes, it will be definitely helpful for your NEET. Just trust me, because all the sessions in organic chemistry which I will be taking will cover all your, say NEET paper, or you can simply say NEET paper will be around these sessions or these concepts only. But you have to be with me, you have to be very much sincere. Okay, thank you Arjun, thank you Mohan Raj, thank you, God bless you, thank you Akshaya, thank you everyone. So let's meet on Sunday. Till then, take care, God bless you and love you all. So good night.